Now let's continue on with our algebraic proofs. I'm hoping that you have your best guess on 1 through 10 using the Cornell notes, and bring those to class with you tomorrow, and you and your partner can decide on exactly what the final answers will be to submit to me in class. So moving on to the algebraic proofs, we're going to start applying all those properties as we work through these algebraic proofs, using something we're familiar with, solving equations, and just adding that right side to justify each of the steps. So let's go ahead and put another line here to make our table. This is where your statements go. This is where your reasons go, but you don't need to write statements and reasons above them. That was just to show you. Now the first step on the left side, the first statement is always going to be a given in this case, because that's what we're beginning with. There are very few exceptions. We're almost always putting one of our givens into the proof right away. So the only reason we know this to be true, 3 times the quantity x minus 2 equals 42, is because it's given to us. What we're trying to prove is that x equals 16. So the only reason we know this is true is just because it's given to us. So we will write given. It's given to us. Okay? Now, as we move through solving each of these equations, there are sometimes different ways to go about doing them. In this case, there's actually 2 different ways you could do this. I'm assuming that most of you will probably choose to distribute the 3. So when we distribute the 3, we get 3x minus 6 equals 42. Now, there are properties, other properties that you can use: addition, subtraction, multiplication, division, distributive property. So as you move through these algebraic proofs, if you find that one of these things works for the examples at the top, you can go back and change your answers if you'd like. So we do also have some other properties. We can go ahead and write them. We can write them here at the top. Now, the reason I didn't go through them is because they are things that we've already been using. Addition, when you add the same thing to both sides of the equation. Subtraction, when you subtract the same thing from both sides of the equation. Multiplication, when you multiply both sides of the equation by the exact same thing. Division, when you divide both sides by the same thing. And also distributive property, which is what we are using on this problem here. So when we distribute that, step 2 then would just be distributive property. Okay. Now, what would you do next to this equation to help you solve it? All right, you would probably add 6 to both sides. Now, in this particular case, we are adding 6 to both sides, and you can make a miniature version of that if you want to write it, or you can skip writing it altogether. That's not going to be a separate step. When we add 6 to the left side, we get 3x. When we add 6 to the right side, we get 48. And so the reason that we can go from step 2 to step 3 is addition. Addition property. Okay. Step 4, what do we need to do to both sides to get x alone, to get to the point of x equals 16 at the end of our proof? We're simply dividing both sides by 3. You don't have to show that, I'm just showing it in case you need to see it. We divide this side by 3, we get x, and we divide this side by 3, we get 16. And so that would be division, because we divided both sides. And now, what you'll find is this should always be, your last step should always be exactly what it says we're trying to prove. So this is where we're starting from, this is where we need to end up, and then these are the steps we had to take in between to get to that spot, and we're just justifying how we are allowed to do each of those steps, what allows us to do each of those steps. So we use properties and postulates and theorems and eventually definitions to help us move through each of these steps. So this is something on the left side that you already know how to do. We're just adding some other pieces here, okay? Number 2, we'll do number 2 together. Now number 2 has fractions in it. So again, with these proofs, there's more than one way that you can go about these proofs. When I teach algebra, I always teach eliminating the fractions as quickly as possible because nobody likes to deal with fractions. So let's begin. The given needs to be in this first step. 7 halves minus n equals 4 minus 1/2 n. That's our given. All right. Now, if we multiply the whole entire equation by something, we could get rid of all the fractions in the first step. What is it that we're going to multiply the whole entire equation by to get rid of all those fractions? 2. Yes, we can multiply everything by 2. So if I multiply this piece by 2 over 1, this by 2, this by 2, and this by 2 over 1, the 2's cancel here and we just get 7. 2 times n is 2n. 4 times 2 is 8. And 2 over 1 times 1/2 n. The 2's cancel, and if you want to cancel the 1's, you can, but you're left with just n. So what did we do to get from step 1 to step 2? We multiplied. So that property is multiplication. Right? Now, our goal is to get to n equals -1. So what would we need to do to help us start reaching that goal? Again, there's a couple different ways that you can go. None of them are wrong. You just need to make sure your reason matches up with the step that you took. So I generally suggest that we move variables first. And again, you can move your variables to the right or you can move your variables to the left. I'm going to move them to the right just so I can show you how to use one of the properties. So we're going to take this -2n and add it to both sides. Again, you don't have to show that step. I'm just showing you so you can see it if you need to. So these will drop out and we'll have 7 equals 8. And this is a 2n minus an n. So that gives us just a positive n, 8 plus n. So what did we do? We use the addition property. All right. We're going to continue to get n alone by moving this 8 back. So we're subtracting 8 from both sides. 7 minus 8 would give us -1. These drop out and we get -1 equals n. And what's that property? Subtraction, because we subtracted 8 from both sides. Subtraction property. Now, here's the thing. Does this look exactly the same as what we were trying to prove? No, it needs to look exactly the same as what it says in the prove statement. That's our ultimate goal, and this does not look like that. So we need to take one more step to flip this over, n equals -1. Now, can you remember which property that is? The property that allows you to just flip a statement over, an equality. That's going to be our symmetric property. This is not the only way to do this equation. There's several different ways to do this proof. So if you collected your n's on the left side, you would never use a symmetric property. That doesn't mean it's wrong. It's just another way that you can solve the equation. So sometimes these are harder or take a little more time to grade because there's more than one way to go about it. And that's the same in a geometric proof. So just because my answer says one thing and yours says something different, it does not necessarily mean yours is wrong because there's several ways that you can get through it. Okay, what I'd like you to do is pause here and try to do number 3 on your own. All right, work through the steps, and you're going to have a left side and a right side. Now, keeping in mind, I can't even tell you how many steps there are because there's different ways that you can do this proof. So I'll get you started. Number 1 should be your given right here. And at the end here, of course, you should have x equals 3. We don't know how many steps that takes, so you can't put a number here just yet. So I want you to complete this proof and bring it to class tomorrow. And we will discuss it when you get to class tomorrow. I'll be checking for that, so make sure you have finished that one. But let's move on to 4 and 5. 4 and 5 are a little more challenging, and I'm not expecting you to try those on your own by yourself. So I'm going to work with you on these two, and then you're going to bring number 3 back with you to class. Now, number 4, you can see, now moves us into some geometry. So it's kind of a combination of using an algebraic proof for a geometric diagram. Okay. Now this will take 6 steps, so you want to make sure that you do write somewhat small so you can fit it all in. Okay. Now number 1 is going to be our given. Now as we write it in here, we also want to label this. So the measure of angle ABC plus the measure of angle CBD equals 90 degrees. Now, you wouldn't be required to draw this, but if you're looking at this ABC and CBD, if they add up to 90 degrees, then you technically could mark the corner here as a right angle for 90 degrees, or which we'll also talk about being perpendicular. So let's go ahead and put a first given in here, the measure of angle ABC plus the measure of angle CBD equals 90 degrees. That's our given. Now we can't do anything with that unless we have these other 2 given pieces for us. So we're going to write all 3 givens into the same step. And since the reason for all 3 statements is given, we can include them all into one step. Okay, so this is our first step, number 1. So we're going to squeeze the rest of them. What we're trying to prove is that x equals 27. Now, we've got to pause for a moment and look at what we've got. And it's helpful if maybe we take, you should always label your diagrams. That's one of my number 1 rules. The measure of angle ABC is 3x minus 5. So ABC is 3x minus 5. And CBD is x plus 1 over 2. Now, if we know ABC plus CBD equals 90 degrees, and we know the measures of each of these, then that means this one plus this one better also equal 90, okay? So what we're going to do, since we know ABC is equal to 3x minus 5, we're going to take 3x minus 5 and put it in place of ABC. So we get 3x minus 5 plus. In the same token, if we know that the measure of angle CBD is x plus 1 over 2, then we're going to take this x plus 1 over 2 and plug it in for this guy. Okay, so ABC, ABC, we took this guy and plugged it in for that ABC. And if CBD is equal to x plus 1 over 2, instead of writing CBD, we write x plus 1 over 2. And we took this and put it in place of this other one. What property involves putting something in place of another one that is equivalent to or equal to, or plugging it in? That's the key word there. That is going to be an example of substitution property. We're plugging in measures that are equal to those angles. So this is where we are. And now this is strictly an algebraic proof. If we utilize what we used on number 2, on the number 2 algebraic proof, we want to get rid of these fractions first. So what we want to do, Get rid of all the fractions by multiplying every single piece by the denominator, which is 2. Times 2, times 2, times 2 over 1, times 2. So 3x times 2 gives us 6x. 5 times 2 gives us 10. Here, the 2's will cancel and you just get x plus 1. And 90 times 2 is 180. And I'm going to drop the degrees off so we don't get confused either. So we multiplied every single piece by 2, so that's multiplication property. Okay. Continuing on, we want to get x equal to 27. So what do we need to do? There are, I told you there are 6 steps. So if you're working this out on your own, you could possibly do it a much longer way. In order to keep it short, what you want to do is go ahead and combine like terms. You want to simplify this whole left side before you start moving anything around. So in step 4, we want to simplify 6x plus x would give us 7x. Negative 10 plus 1 would give us negative 9 equals 180. So what was it, what property was it that I told you was combining like terms? That's another substitution property. Remember, there's 2 versions of substitution property: plugging something in to something that it's equal to, or combining like terms, because you're still taking these 2 guys and plugging something in place of them. All right, next we want to move that 9 over, so we're going to add that 9 to both sides, so we get 7x equals 189. And since we added 9 to both sides, that's addition property. And number 6, we simply need to get x alone. So we divide both sides by 7, so we get x equals 27. And that would be division property. Sorry, I'm writing all over that picture. Okay, so the first step was a new idea, and it's not a new idea, but the first time we've plugged these into an algebraic statement. I'm sorry, a geometric statement. The rest of it then is just like the others. Okay. Now, number 5, I'm going to help you with. I'd have you try to do it on your own, but we have a definition here that is a foreshadowing of one that we will get to. I haven't gotten to it yet, so I'm going to go ahead and do this one with you also. It says that BY bisects angle XBC. Now, bisecting is a definition that we haven't written down yet. So let's go ahead and grab our Cornell note sheet. We'll go ahead and define this since we have the time. Definition of an angle bisector. Here's what we're talking about. If we've got an angle, bisect, if we bisect an angle, think what that sounds like. Bisect. It sounds like dissect. Okay. Now the bi, like bicycle, means 2. So sect means to cut, and bi means 2. So the idea is that we're cutting it into 2. Cutting it into 2. Bisect. And the most important piece of that is that we're cutting the angle into 2 congruent angles. And to show that they're congruent, we use little arcs to show that they're congruent like this. So this is what the statement might say. If our angle, ray BD, no, we should go ahead and, this is A, B, C, and there's ray BD. If ray BD is the angle bisector, then angle 1 is congruent to angle 2. So if BD is the angle bisector, that means it is the thing that is bisecting, cutting it into 2 equal angles. Therefore, these angles are congruent. This can also work the other way. If angle 1 is congruent to angle 2, then ray BD must be the angle bisector. So we will revisit this and spend lots of time on this, but this is the definition that we need to use on this proof here. So I needed to make sure that we got that written down. All right, so number one is going to be our, what I call our wordy statement. Ray BY bisects angle XBC. And that is, of course, given. Now, if we know that BY bisects angle XBC, then we know that these two angles must be congruent because it's cutting it into two congruent angles. So we're going to mark these two angles congruent. We also know the measure of angle ABY is equal to 11x plus 5, and the measure of angle YBC equals 10x plus 1. So those are all our given pieces. So here is where we need to, what I say, undo the wordy statement. This is a wordy statement because it's got words in it. Now what we need to do is take what we put in the picture here and put it into our proof. So we would say angle ABY is congruent to angle YBC. And that is going to be the reason I just gave you. Definition of angle bisector. Okay? Now again, we're going to spend lots more time on this, so don't stress about this. Okay? Lots more time. Now, once we're here, then if we know ABY is equal to 11x plus 5, and YBC is equal to 10x plus 1, okay. ABY is here, it's also here, so we can take this 11x plus 5 and plug it into here, so we get 11x plus 5. And here's YBC, and YBC is equal to 10x plus 1, so we can put 10x plus 1 in place of YBC. So we get 10x plus 1. Now we're putting these things in place of their angles, or plugging it in place of their angles. So that is going to be a substitution property. Putting something in place of something else. And now algebraic. So we get back to the easy stuff here. Again, this is just foreshadowing. We're getting there, so don't stress. We want to get x alone on the left side. So again, there's several ways that you can do this. I'd probably move this 10x over. Subtract 10x from both sides. 11x minus 10x gives us x. And this is not completely accurate because we still need to get into all the semantics of proofs. But congruence and equality are the same idea. For the sake of this being a basic proof, let's just go ahead and change that into equality. You can't technically do that, but we will talk more about that later, okay? The idea still works, we just need a formal step in between here. Then over here, this drops out and we get 1. So we subtracted 10x from both sides, so that's subtraction property. And then we're going to go ahead and subtract. Oops. This is supposed to be 11x. Oh, let's go back. I made a mistake. This needed to be changed to 11x minus 5. So this is 11x minus 5, which makes this minus 5. So we're going to add 5 to both sides, and that gives us x equals 6. So adding 5 to both sides, that's addition property. Okay. Now you see there's a star next to this one. That's because it's difficult. Okay. We will spend lots more time on this. So please, 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 I can't stress it enough that I don't want you to stress over this. This is just going to help us out when we get there eventually. This should get easier and easier, okay? So make sure that you finish number 3. It's a basic proof, just like number 2, and you should have no trouble with that. So bring that in with you tomorrow, as well as your best guess on all of these. Now let me give you There are a couple that you may not know. Number 4, you might have some trouble with. And number 10 is a challenging one. So I want you to try to figure out what that one's going to be. And let me give you one of them. Number 7. I'm going to give you 7. If st equals 10, then st minus 5 equals 10 minus 5. So how's the left side different? It was st, now it's st minus 5. The right side was 10, now it's 10 minus 5. So how do we go from this statement to this statement? We're subtracting 5 from both sides. So this should be subtraction property. Okay. All right, so bring the rest of these with you tomorrow. And if you have trouble with 4, don't worry about that. We will discuss that also. Good luck. We'll see you tomorrow.